Real numbers. Introduction. In the previous class, we have learnt about real numbers which are not rational numbers, and hence the existence of irrational numbers such as √2, √3, √5, etc. In this chapter, we will learn some more properties of the positive real numbers. We will introduce two very important properties of positive integers: Euclid's division algorithm and the fundamental theorem of arithmetic. We will also learn about some of their applications. With the help of the fundamental theorem of arithmetic, we will establish 1. The irrationality of the numbers like √2, √3 and √5, and 2. The nature of the decimal expansion of a rational number of the form p by q, where q not equal to 0. That is, when will the decimal expansion of p by q is terminating and when will it be non-terminating recurring, meaning repeating. For example, decimal expansion of 2 by 5 is 0.4, which is terminating, whereas the decimal expansion of 1/3 is 0.3333, and so on, which is non-terminating, rather recurring. In this chapter, we will learn the logical reasoning for this behavior of the rational numbers of the form p by q, q not equal to 0. Euclid's division algorithm. We are already familiar with the process of long division of a positive integer a by another positive integer b. Let us take a is equal to 37, b is equal to 5, and make the division of 37 by 5 as under. In the above process, division of 37 by 5 gives quotient equal to 7 and remainder 2. It helps us to write the following relation of equality. In the above relation, we have expressed 37 as the sum of two positive integers. One is a multiple of 5, that is 5 into 7, and the other is less than 5, that is 2. Let us consider some more pairs of integers as below. It is not necessary to find the quotient and remainder by long division. We can do it or all and at the same moment write the relation between two numbers as below. It is observed that the quotients are 2, 3, 0, 7 and 3 respectively, whereas the remainders are 4, 2, 4, 0 and 0 respectively. From the above, we can conclude that for each pair of path integers a and b, a pair of whole numbers q and r, such that a is equal to b into q plus r, 0 lesser than or equal to r, lesser than or equal to b. Hence, q is the quotient and r is the remainder obtained when a is divided by b. Some observations about the quotient and the remainder are as below. Let us write some more relations of the form a is equal to b into q plus r, 0 lesser than or equal to r, lesser than b. 1. 47 is equal to 9 into q plus r. 2. 83 is equal to 17 into q plus r. 3. 75 is equal to 15 into q plus r. And 4. 7 is equal to 37 into q plus r. In order to get a feel for what Euclid's division lemma is, consider the following pairs of integers: 17 and 6, 5 and 12, 20 and 4. We can write the following relations for each such pair as shown below. That is, for each of positive integers a and b, we have formed whole numbers q and r, satisfying the relation a is equal to bq plus r, 0 lesser than or equal to R lesser than Q. Euclid's division lemma. Given positive integers a and b, there exist unique integers q and r satisfying a is equal to bq plus r, 0 lesser than equal to r lesser than b. Corollary. Every positive integer is either of the form 3m or 3m plus 1 or 3m plus 2 for some integer m, a whole number. Proof. The proof is shown on the screen.
Note: every positive even integer is of the form 2m, where m is some integer, that is, a whole number. Every positive odd integer is of the form 2m plus 1, where m some integer, that is, a whole number.
The HCF of two positive integers a and b is obtained as below.
Find the HCF of the positive integer 455 and 42 with the help of the division algorithm. Solution. We start with large integer, that is 455, and apply the division algorithm to get 455 is equal to 42 into 10 plus 35. Now, we consider divisor 42 and the remainder 35 and apply the division algorithm to get 42 is equal to 35 into 1 plus 7. Now, we consider divisor 35 and the remainder 7 and apply the division algorithm to get 35 is equal to 7 into 5 plus 0. We conclude that HCF of 455, 42 is equal to HCF of 42 and 35.